What's up, scholars? Mr. Hipschman here. I'm going to run through some more detailed look at each one of the questions on your practice quiz for simple harmonic motion to try to help you get prepared for your quiz over Unit 5, simple harmonic motion. Now, I know we went quickly through this unit. To prepare to go through this with me, I want you to do a few things. First, have your responses to the quiz. Second, make sure you have the solutions pulled up. I'm going to be working on a piece of paper, the same with the answers on it, and I'll post that as well. And then finally, the other thing that's going to be really helpful, because unfortunately none of you likely have spring mass systems at home, I want you to open up the PhET spring mass system that's on Google Classroom. Additionally, I think it may be helpful for you to find your own pendulum. So I've got mine. Where'd mine go? I've got mine around here somewhere. But there's also the pendulum lab. I just use a string of keys to do that. So now that you've got those things open, let's jump right in and start with number 1. One of the most important things to do for pretty much all of these questions in any AP multiple choice question is read it very carefully. Now, we want to be efficient with our time, so we want to try to read it carefully on the first go. So this is the only one I'm actually going to read to you. The rest I'll ask you to pause and read yourself, but this one, let's read it together. So it says a 2-kilogram block on a horizontal surface is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall, and there is a negligible friction between the block and the horizontal surface. The block is released from rest after the spring is stretched, such that the block spring system experiences simple harmonic motion, as shown in the graph that represents the block's velocity as a function of time. So, at that point, all they've done is describe a spring mass system. Let's go ahead and draw that. Just very quickly sketch it. Remember, on these problems, we want to spend between 90 seconds and 2 minutes. So let's very quickly sketch that. They're just describing a block on a spring, and it's just moving back and forth, undergoing simple harmonic motion, and it's moving about some equilibrium position. We can call that x naught. Now, importantly, this is a graph of its velocity. So what we know is it's going to oscillate back and forth between some position over here and some position over here. It's going to stop. The velocity is going to be equal to 0 here and over here, and it's going to be moving fastest in the middle. Now, how do we know that? One of the easiest ways to see that, I know it's not exactly the same, but one of the easiest ways to see that is to look at a vertical spring mass system. I don't have any good way of showing you a horizontal system. But watch what happens. I'm going to do it slowly, and you're going to see, again, it's going to, I'll go it slow, and we'll crank up the mass so it's more dramatic. Okay? So it stops at the bottom here. It's moving fastest somewhere in the middle. You can see the kinetic is biggest in the middle there. Rather, right here, it's biggest in the middle. And then it stops at the top as well. We'll wait until it stops at the top one more time. So to this point, we haven't even gotten to the question. Let's read the question. It says, how can a student use the known information on the graph to determine the magnitude of the change in spring potential energy of the system from release point of the block to the moment when the block's spring potential energy is 0? So all this is saying is, at some point there's going to be a maximum amount of spring potential energy. And the place that's going to be is when the spring is compressed. So if this is the initial length of the spring, when it's compressed to something like this, here's our mass. When it's compressed to something like this, it's got a maximum amount of energy. It's squished the most that it can be. All the spring can do after that is release that energy and move the block over this way. Now, it'll be at a 0, the potential energy will be 0 when the block reaches the equilibrium position again. And as we saw a moment ago, and I'll let you play around with the simulation, that is going to happen when it reaches the middle. Another important thing to think about here is we're just talking about conservation of mechanical energy. So mechanical energy is equal to potential energy. In this case, it's just spring potential or elastic potential plus kinetic energy, the energy of it moving back and forth. So what we need to do is we want to know the maximum amount of spring potential energy, and that's going to, the easiest way to find that is to look for a place when the kinetic energy is at a maximum. Let me show you why that is. If we look here at our graph, at this moment the velocity is at or the speed rather, it's negative, is at a maximum. So it oscillates between -5 and 5 and -5 again, and it will keep doing that. So we know that if we draw our little energy pies, this is going to be all kinetic energy here, okay, and it's going to oscillate back and forth between having maximum kinetic and maximum potential. Here there's no potential energy. It's moving as fast as it can go. The spring is completely relaxed. Then the next moment we start to build up potential, and then when it stops, again it'll stop somewhere over here, the potential energy will go to 0, just like this, okay? And it's going to go in between. Now, what's lovely about this, I'm going to make up a number. Let's say the kinetic energy at this moment is 100 joules, right? I'm just making that up. That's not true. Right? Actually, I'm going to erase that. I don't want people to get confused. That is not the total amount of energy. But let's just say it was 100 joules. That means that it's going to be 100 joules here as well because of conservation of energy. So the basic scheme that we can use is we want to find a place where we know the kinetic energy, and that will tell us the potential energy. Now, it's a weird question because it's not actually asking us to do any calculations. So with that in mind, let's look at the answers here. That's going to be helpful here. Let's look at the answers. Determine the kinetic energy of the block at 8 seconds using the kinetic energy equation. That's not going to work. The reason that's not going to work is that the velocity is equal to 0 there. So the kinetic energy would be 0. That would make us think that the total potential energy and the maximum potential energy is also 0. So we're just going to do an elimination of A. Now we know it's B. Let's skip over B for just a moment for right now. This says determine the kinetic energy of the blocks at 2 seconds and 6 seconds and add the two values. So, okay, this would give us the kinetic energy. This would give us the kinetic energy at some later time. Answer choice C is basically saying double the total energy in the system. So that's kind of nonsense. Let's look at the next one. It says the same thing but subtract them. Okay, we'd have a total amount of energy here, a total amount of energy here, and if you subtracted them, you would get that the total energy is again 0. So D is nonsense. The only thing that's left is B, so we could pick that by default, but let me show you, in fact, why it is B. So it's B because here you could find the total kinetic energy. Again, let's just pretend for right now that it's 100 joules. That would be the potential energy, or the difference between the potential energy from its maximum to when it is 0. Now I know the question is worded in a funny way. I hope that breakdown was helpful on that.